Alright, silly people, here's the situation. This time we're going to be applying this formula over and over again that Griffiths calls the generalized Ironfest's theorem. Just that if you take the explicit time derivative of an expectation value for an operator that represents some physical observable and some Hamiltonian, it has a predictable result in I over h bar times the expectation value of the commutation between that Hamiltonian and your operator plus the expectation value of the partial time derivative of your operator. So that's interesting. We're going to be doing it for a couple of different operators and then commenting on the results. And the first one that Griffiths wanted us to talk about was Q equals 1, which isn't really an operator, it's just a number. So we're going to be taking the explicit time derivative of 1, and that should be equal to I over h bar, expectation value of Hamiltonian commuting with 1, plus the partial time derivative of 1 and an expectation value. So the time derivative, or the expectation value of 1 is just 1, and then the derivative of that is 0. Since 1 is just a number, it's going to commute with any other operator, so the commutator of that is just 0. And then the time derivative of 1 is also just 0. So we found that 0 is equal to 0. And the way that we're supposed to interpret this is that 1 represents a normalized state, pretty much. That 1 is always equal to the square modulus of an exponent or of a wave function here, integrated over space, right? That's kind of just a rule that you learn. So in taking the time derivative of this, treating it as an operator, we're kind of trying to prove that if you pick a normalization scheme for a wave function, or you find a normalization scheme based on the wave function itself and its boundary conditions, that normalization is a constant. If you apply any operators to that at all, you're going to get back out the same normalization to the system because you're not changing anything about it except for trying to observe it. So that's supposed to represent conservation of normalization scheme. If you don't quite see it, don't worry, I have a problem seeing it too. I don't think Griffiths was cooking with gas on that one, but we'll keep going. What if the operator was the Hamiltonian itself? So d dt of the expectation value of the Hamiltonian is equal to I over h bar times the expectation value of the commutator between the Hamiltonian with itself plus the partial derivative of the Hamiltonian with respect to time. So the expectation value of a Hamiltonian, you guys know, is just the energy value of your system. So this is dE dt, what you expect your energy to be for a system. And then the Hamiltonian, since it's an operator, does just commute with itself. So you got the expectation value of 0 here. And then typically your Hamiltonians don't depend on time. So you've also got a expectation value of 0 here. If you wanted to talk about explicit time dependence in your Hamiltonian, that's a whole other video. But you get 0 on the right-hand side is what you're trying to see. So dE dt equals 0. That's supposed to be conservation of energy. We just proved conservation of energy just by applying this Ironfest's theorem thing. The change in energy over time is 0. Kind of cool. So we can keep going from there. What if the operator was x, just x? So you're talking about the time derivative of the expectation value of x should be equal to I over h bar expectation value of the commutator of a Hamiltonian with x plus the explicit, or times the partial derivative of x, right, with respect to time. So I think you can rationalize in your brain that the time derivative of the expectation value of x is the expectation value of the particle's velocity. So just the particle's velocity there. And then for the Hamiltonian, the part of the Hamiltonian that doesn't commute with x is the p squared part. So I'm going to expand this into expectation value of 1 over m times the commutator of p squared with x. Whoops. Yeah, that's right. And then typically your x won't explicitly depend on time either, so the partial derivative of that is 0. And then, so we've got, I'm going to move the 1 over 2m out as well, so we've got 2m h bar on the bottom here, but it's the expectation value of, and then I kind of did this in one of my more recent videos, but you can split up this commutator into p times the commutator of p with x plus commutator of x with p times p, and then the commutator of x with p is the canonical commutation relation, except since it's p with x instead of x with p here, and I should specify this is also p with x, that whenever you flip the order of the commutator, you get a minus sign. So this is minus I h bar p, and this is minus I h bar p. So I'm just going to get rid of the minus sign there. Minus I h bar p. And then if you factor out that I h bar, and also add up the fact that you've got 2 factors of I h bar p in there, you should just get the expectation value of p over m, right? So if you then move the m to the other side of the expression, you've got that mass times expectation value of velocity is equal to the expectation value of p. That's also just a specific example of Iron-Fest's theorem that has already shown up in a problem elsewhere. Yeah, you could easily extend this to the idea of Iron-Fest's theorem for kinetic energy as well, if you just did m over 2 times v squared, just multiplying it by the expectation value of v over 2, which is a constant, will be equal to m, or just, yeah, p over 2 squared. But all right, let's keep going. The last one that he assigned us is the operator is going to be equal to p. So we're talking about the derivative with respect to time of the expectation value of momentum is equal to I over h bar expectation value of commutator of h with p. So, and then that will be plus the partial derivative of momentum with respect to time. So I'm going to keep the left-hand side the same. There's nothing really fancy we can say about that. But this here, the part of the Hamiltonian that commutes with momentum is the potential. So this is actually just v of x with p. And then momentum, we're going to assume that it doesn't explicitly depend on time either. So we've got I over h bar. And then in a previous problem, we know that the commutation of f of x with p is always just I h bar df dx. In this case, it's dv dx, since it's the potential that we're talking about. So we can move the factor of I out, we can move the factor of h bar out, so we'll get an overall minus sign with our dv dx here. And this is another instance of just being a equation that has shown up previously in the book, also being called Iron-Fest's theorem, but in this case it is an explicit reference to the partial of the potential with respect to x is this. So it's kind of interesting. All right.